start. It's 10:03. Good morning, everyone, and welcome to the fourth lecture of this course, Vector Space Linear Algebra. So we'll do a quick recap of what all was covered till now. Um, so first we started with some basics of abelian. What is abelian group? What is a field, and so on. We define these algebraic structures, that is, with some set of objects and some operations and some properties. We can define these basic concepts, right? And then we use that definitions to define what is called as a vector space, right? Where we have its own operations, and mainly two operations. One is your vector addition operation, and one is the scalar multiplication operation, right? And post which we then went to something called as subspaces. Subspaces are basically subsets of a vector space, which are vector spaces in among them in themselves, right? So and we saw a very important theorem in the subspace expansion theorem, that is, for example, the subspace spanned by a non-empty subset of a vector space is just a linear combination of vectors in that particular set, right? And then we started with we saw something called as basis and dimensions. We define what is linear dependence and independence, and some consequences of the definition. We mainly define what is a basis, and how do you define and how do you come to something called as dimension of a vector space, right? So using this property, we looked at some very basic concepts of basis. For example, your Rn as a vector space, right? And vector space of all polynomial functions, and so on, right? Right. And then we came to this idea where we say that if V is a vector space spanned by a finite set of vectors, then any independent set of vectors is finite and contains no more than m elements, right? This will be useful for us to prove further concepts, which we might do it today. Then we saw a quick intro of linear transformations, right? How do you define a linear transformation? And the properties of a linear transformation. We saw that differentiation, integration, all those can be seen as linear transformations, right? More importantly, we saw also the matrix multiplication as a linear operation, and we'll connect all the ideas to matrices going forward at the end of this course, right? And then we saw this important theorem which said that if you have any ordered basis for any vector space, and we have a transformation T which goes from V into W, then there is a unique transformation which converts these basis to any vectors in the W space, in the codomain space, right? Now this is important because this helps us understand if you want to define a transformation, if you want to go from one space to another, what you need is just the dimension of the domain, right? So if you have that many number of vectors, you're set to define a unique linear transformation. All right. And then we saw some of the important subspaces, range of T and nullity of null space of T. And then we defined something called as rank of T and nullity of T. They should already be a bit familiar from the matrix theory. If not, we'll again connect all of these ideas to matrices. And then we saw a theorem called as rank nullity theorem. We are yet to prove it, and we'll prove it hopefully today or tomorrow's class. All right. So we'll now jump ahead and we'll start with something called as algebra of transformations. All right. Where we define, let's say we have two transformations, right? Let's say T and U. So how do we define something called as addition or multiplication or composition and so on, right? See, at the end of the day, transformations are basically functions, right, which move from one space to another. So can we define operations which we define on functions in the same way on this transformations, right? So given that T and U are two transformations which go from the same V to W, then we define this T plus U, the addition of two transformations, as just the result of the addition of the two transformations applied uniquely, independently, right? And this ct, the scalar multiplication with a particular element f, right, is defined as c times t of alpha, right? See, this f is basically a common across both the fields, which we know from the definition of linear transformation, right? So f is over which both v and w are defined, right? It is essential because otherwise this product will not be well defined, will not be defined, right? So now let's consider tau as a set of all linear transformations from v to w, right? So if tau is a linear transformation, a set of all linear transformations, if you see these operations are basically taking two elements of tau, right? Some elements t and u, right? And we are defining an operation on that set tau. And we also have this c, which is a scalar multiplication operation being applied on the elements of tau. So basically, if you see here, um, we have this tau with these operations, that is tau comma plus comma the scalar multiplication, right? This is basically a vector space in itself over the field f, right? Over the field f. See, tau is basically set of all transformations, okay, which are basically going from one vector space to another vector space, which are defined over the same field f. What ends up happening is all of these transformations, this set of all these transformations, they end up being a vector space among themselves and over the field f. Now this shows the power of vector spaces. So you can actually look at something which is defined over f, right, as a vector space in itself, right? So the proof of this is basically will be a straightforward thing. What we need to do is we just need to see whether right, whether this set is a vector space. So how do you prove something is a vector space? We have these operations, right? We have these four properties of abelian, that is tau comma plus has to be an abelian group, and tau comma dot has to satisfy some properties, right? So tau comma plus is basically for abelian, first we need is closure, right? So you need to prove that t plus u, right, is a linear transformation, right, which is again a straightforward thing, right? Because if you see t plus u times c alpha plus beta, okay, this will just become t of c alpha plus beta plus u of c alpha plus beta, which is just c times t of alpha plus t of beta, okay, plus c times u of alpha plus u of beta, right? And then this becomes c times t of alpha, t plus u of alpha, just of alpha plus t of u of beta, right, by definition. So therefore you can see that this t plus u is a linear transformation, right? So if you take any element like this, what you get up is what you end up getting is c times the element applied on t plus u plus t plus u times beta, t plus u of beta, right? So okay, so this is fine, and then we have other things. For example, let's say is it associative, right? For example, let's say if I have three linear transformations, right, is this sum, right, equal to t plus u times plus z, right? So again, straightforward proof like this one you need to prove. This is again straightforward. Then we have this idea of commutative, that is t plus u should be equal to u plus t. Again, similar sort of a proof. What we need though, two major things, is that can we define something called as inverse and identity, right? So identity in terms of your plus operation, right, it has to be a zero operation, right? Because I mean some zero operation. So what we need is we need something like this: t plus 0 of alpha has to be equal to t of alpha, right? Only then 0 of alpha would become a identity over this vector space tau, right? So if you want to do this, what this means, right? So this means that this should be so again applying this definition of t plus u. So t plus alpha, t of alpha plus 0 of alpha is t of alpha, right? Now t of alpha is a vector in W space. O of alpha is also a 0 of alpha is also a vector in W space, right? So the inverse exists for t of alpha. I just add the additive inverse of both of them here, right? So what will happen, and what will end up happening is I get 0 of alpha is equal to 0, right? This is the zero vector of W space, W vector space, right? So so therefore this particular transformation 0 of alpha is equal to 0 is a vector space in is the zero vector in this vector space of all linear transformations, right? Now we need to see whether this is a um, uh, uh, linear transformation or not, right? Because this needs to be an element of this set tau, right? So how do you go about doing it? Again, straightforward. So you can just say C alpha plus beta is equal to C times 0 of alpha plus 0 of beta, right? This is equal to C times 0 plus 0. C times 0 is 0, 0 plus 0 is 0, right? So this is also a linear transformation. Okay, so you can write this 0 of yeah, this is basically C times 0 of alpha plus 0 of beta, right, from definition. So therefore this is a element of this set tau, right? And hence you can get this. Now yeah, so what we need is basically the inverse, the additive inverse of this element t, right? So basically what we need is something like t plus, let's say if t inverse in this case, okay, we'll not use t inverse, let's use something like z, okay, of alpha should be equal to 0 of alpha, right? By the definition of inverse. Now 0 of alpha we know is always 0, and this we know is t of alpha plus z of alpha, again by definition is 0. So this implies that z of alpha is equal to minus t of alpha, right? So if I define a transformation z, okay, such that any z of alpha becomes minus t of alpha, right, then basically I have defined a transformation which is the additive inverse of t, right? So therefore with all these operations I can say that tau comma plus is an abelian group, right? Is an abelian group. Then what we need to show is we need to use the other properties on the scalar multiplication operation, right? So what we have is, first thing is we need to show that 1 times any t is t, right, for any t belonging to tau. So this one is basically the scalar, the scalar in the field f. Now this is true because 1 times what is t of alpha should be equal to t of alpha, right? Now t of alpha is a vector in W, right? And we know that W is a vector space over the same field f. So 1 into any element in W will be equal to the same element, right? So therefore this is true by definition. Then you have other properties, for example, C1 C2 dot t should be equal to C1 dot C2 dot t, right? Okay, and then we have the properties of distributiveness, right? So if I have C dot t plus u should be equal to C dot t plus C dot u, and C1 plus C2 dot t should be equal to C1 dot t plus C2 dot t, right? So again, all this straightforward proof from follows from the fact that the t of alpha, which is the range, the codomain of t, is W, which is a vector space. So all of these end up just becoming operations on the vectors in W space, which are all well defined. Okay, so with this we see that tau comma plus comma dot defined in the above way, right? This addition in this way, hence scalar multiplication in this way, is a vector space, right? Is a vector space, right? And it's over the field f, because all of these all of these scalars that we use to prove all of this is actually from the field F, right? So vector space over the field F. Okay, good. So this is the basic idea. Then we have something called as so now we define something called as composition operation. So we already know like what the function composition is, right? For example, let's say if I have, we already discussed this in the first class. So if I have two functions f and g, the composition is defined as f circle g in this sphere, right? So we say f circle g of x is basically f of g of x, right? So whatever g spits out, f takes that as input and again spits out some element that is the element corresponding to x under the mapping f circle g, right? So similarly, we define this composition of these two operations ut. So let's say I have this t which goes from v to w, two vector spaces, and u goes from w to z, be some linear transformations. This ut composition of alpha is defined as u of t of alpha, right? So which kind of makes sense, because see, t of alpha is going to give you a vector in w, right? And u takes a vector in w and puts it to vector in z, right? So what we need to prove is that ut is linear in nature, right? So how would you go about proving this? Basically you need to prove something like this, right? As from definition, that this is equal to ut times c times ut of alpha plus ut of beta, right? Now this is equal to, again by definition here, u of t of c alpha plus beta, right? Now this is equal to u times, this we know is c t of alpha plus t of beta, right? This is equal to u of any combination like this, right, is just going to be c times u of t of alpha plus u of t of beta, right? Which then comes out to be this by definition ut of alpha plus ut of beta, right? So we have proved that ut is linear, right? So transformation composition, that is linear transformation compositions are also linear in nature. Okay, so this basically has a a consequence in matrix multiplication, right? We already saw that if I define some transformation like this, t of alpha is equal to a alpha, right, where alpha is a vector in some fn space and a is a matrix in fm cross n space, right? Vector space, right? So the t of alpha defined in this way is also a linear operator, linear transformation, right? So now what we can do is, if I define a transformation u of beta, something like this, b beta, let's say, where b is a matrix in f cross, let's say p cross m or something, right? P cross m. So then ut of alpha, right, would then basically by definition become b times a times alpha, right? This is also a linear transformation, right? Linear transformation. So if I take two matrices a and b, right, their product is also going to be linear transformation, right? So a b, again obviously with the fact that they are matrix compatible, matrix multiplication compatible, right? If this happens, then this also defines a linear transformation on the space of fn. Okay, fine. Now with this we go to a small definition. We say that linear operator is basically some linear transformation from v into v, that is from the same set to same set, right? So let's say if I have a t which goes from v to v, then we say that t is a linear operator on v. Okay, linear operator on v. Okay, it's from v to v. Okay, now we define something called as invertibility. So let's say I have a transformation t which goes from v to w. We say that it is invertible if and if there exists another u, okay, another transformation u, which goes from w to v, such that ut, which is again an operator on v, and tu, which is an operator on w, are identity, right? So what do you mean by identity? Identity is basically an operator on a vector space v, such that I of alpha is equal to alpha, right? This is the definition of identity operator. What we need to what we need to see is that if there exists another linear transformation, which when composited with this t gives us a linear operator, right? And yeah, if this happens, then we say that t is invertible. Okay, so one thing, if you want to see, so what does this imply, right? It implies that for all alpha in v, ut of alpha is equal to alpha, right? Because ut is again entity on v, right? And then for all beta in w, tu of beta has to be equal to beta by definition, right? Now I say that, so let's say if I have two vectors alpha 1 and alpha 2 in v, such that alpha 1 is not equal to alpha 2, okay, but t of alpha 1 is equal to t of alpha 2 is equal to beta, okay. So these two are not equal, but their image or the result of applying this t is equal, right? Okay, so yes, so let's consider this case and we'll see how it plays out. Okay, so by the way, what does this mean? By the way, this means that t is not 1 1, right? Because two elements in its domain, that is alpha 1 and alpha 2, have the same image beta, right? So it is not 1 1. Okay, so if t is not 1 1, what will happen? So we know that ut of alpha 1 is alpha 1, ut of alpha 2 is alpha 2, which is fine, which means that u of beta has to be alpha 1 and u of beta also has to be alpha 2, right? Which can never happen. See, u is after all a transformation, right? Which is a function. A function cannot have two images for the same element, right? Two images for the same element, right? So therefore, if alpha 1 is not equal to alpha 2, this implies that t of alpha 1 cannot be equal to t of alpha 2, right? Therefore, t has to be 1 1. Okay, so what we are saying is, if an inverse has to exist, right, then that has to be, the t has to be 1 1 compulsorily, right? Because if it is not 1 1, then this sort of an issue will come, which violates the property of getting a identity operator. Okay, good. So this is the one property. Second property, we are saying that, okay, let's say, consider that, so there's some beta in w, right? And we say that u of beta is equal to alpha, right? Which is in v. So what does this mean? This means that t of alpha is equal to beta, right? Why? Because we know that tu of beta has to be equal to beta, right? And u of beta we know is alpha, so t of alpha has to be equal to beta, right? So what we're saying that, okay, beta is some vector in w, right? That vector also has to be an image under t, right? So every beta in w has a pre-image in alpha, a pre-image in t, right? Every pre-image in t. Let's go at alpha, right? So that means t is onto, right? T has to be onto. So if an inverse has to exist, t has to be onto. Okay, this is the second property. Okay, now we'll go ahead and prove that u is unique. Okay, that is, let's say if t is invertible, then this inversion operation, the inverse transformation that we have defined u has to be unique for any given t. Okay, that is the next thing. So here we'll see that prove that t is unique. So suppose that it is not unique, right? So what does mean? That means there exists some, let's say u dash, okay, which goes from w to v, such that u dash t and t u dash are identity, and u dash is not equal to u, right? This is again by definition of inverse operation, inverse transformation, right? So which means that, see, if u dash is not equal to u, that means there exists at least one vector beta in W, such that u dash of beta is not equal to u of beta, right? Because these two are not the same. So at least in one vector, their operation will be different, right? So, but okay, then we know that since t is 1 1, we have already seen that t has to be 1 1 for it to be invertible, right? So, hence we can say that tu dash of beta will not be equal to tu of beta, right? Because we know that if alpha 1 is not equal to alpha 2, we know that t of alpha 1 will never be equal to alpha 2 if t is 1 1, right? By definition. So, hence we have this because t is 1 1. Now tu dash is basically identity, and t is also identity, right? From the previous definition. This means that beta should not be equal to beta, which is a contradiction, right? So hence we say that u is unique. Okay, so we say that if t is invertible, this implies that t is 1 1 on 2 and unique inverse exists. Unique inverse exists, right? And the opposite is also true, right? Let's say if a unique inverse exists, that means the t is invertible, right? So hence this is true. Okay, so we're saying that for a transformation t which is 1 1 on 2, there exists a unique transformation t inverse as a t inverse is equal to t inverse t is equal to I. Okay, see, the thing is, but be very careful on what these operations are defined though. Okay, let's say if t goes from v to w, okay, t inverse is defined from w to v. Okay, so t inverse is going to be an identity over w. T inverse t is going to be an identity over v, right? So be careful on what is the domain and codomain of these transformations defined. Okay, the t inverse is defined on w, and t inverse t is defined on v. That is the difference here. But otherwise, so the main idea here is that if a transformation is 1 1 and on 2, then there is a unique transformation t inverse which satisfies these properties. All right. Then we'll come to something called as non-singular linear transformation. So this definitely, how do we define this? Is that, let's say we have a transformation t which goes from v to w, right? If we can say that t gamma equal to 0 implies that gamma has to be 0, right? If this is true, then we say that t is a non-singular linear transformation. Okay. Now, if you see here, that is basically we're saying that if the null space of t is just a 0 vector, right? So for any vector, let's say alpha not equal to 0, t of alpha will not be equal to 0, right? We're saying this basically. So if this is true, we call t as a non-singular linear transformation. Okay. Now this implies that if t is 1 1, then t is non-singular automatically, right? Why? If t is 1 1, we know that if alpha 1 is not equal to alpha 2, this implies that t of alpha 1 will not be equal to t of alpha 2, right? Now, since this is true, if let's say alpha 2 is 0, right? Let's say if alpha 1 is not 0, this implies t of alpha 1 will never be 0, right? So by definition, we see that if t is 1 1, then by default t is non-singular. Okay, the inverse of this is a bit different to prove, and we'll see that if time remains today. Okay, so we need to see that if t is, so the forward direction is proved, reverse direction we will do it today if time remains. Okay, cool. Now moving ahead, we have a theorem. Okay, yeah. So we I'll just state these theorems, and then we'll go to eigenvectors and spaces, and then we'll circle back to bases and dimensions. Or some ideas are pending there. Okay, so let's say we have a transformation T which goes from V to W, which is a linear transformation. T is non-singular if and only if T carries each linearly independent subset of V onto a linearly independent subset of W. Okay, so we're seeing that if T is non-singular, that means T is like this, that is the null space of T is just a zero vector, right? If this is true if and only if T carries each linearly independent subset of V. So let's say I have a alpha 1 to alpha n is a linearly independent subset of V, right? That so if this is a linearly independent subset of V, and then T carries them to a linearly independent subset of W. What does that mean? It means if I apply this T operation, a T transformation on these elements, T of alpha 1 up to T of alpha n, this is a linearly independent subset, and this will be of W, right? Because T maps vectors from V to W. If this happens, if T is something which preserves this sort of operation, this sort of a property, then T is non-singular. Okay, this is one theorem. Second theorem, what we'll look at is let V and W be finite dimensional. Okay, such that the dimensions are equal. V and W have the same dimensions. Now, if T is a linear transformation, then following are equivalent. T is invertible, T is non-singular, and T is onto. Okay, see, we saw previously that for invertible, if T is 1 1 and onto, then it is it's invertible. We're saying that if the dimensions are equal, then we don't even need both the conditions. We just need one of these. We just need one condition, that is it being either 1 1 or onto, and then we can say that T is invertible. Okay, so in some sense this is very powerful theorem, because then it tells you that if you have two spaces which is the same dimension, if you can find out a transformation which is in some way non-singular, some way 1 1, right, then you will be able to prove you will have that T to be invertible. Okay, so this helps basically when you're trying to change basis from one space to other. For example, let's say Rn space is there, uh, which has its own basis of all these unit vectors, right? We saw that all the EIs, such that all the ith element is 1 remaining or 0 and so on, right? So if you want to change the basis, for example, to some other system where I have defined some other vectors I equal to 1 to n, as long as I can prove that the subspace spanned by this is also of the same dimension, that is n, right, then I will have the operation from going from this basis to this new set of bases, new set of vectors. It will be invertible. So if you have any point, any vector here in this space, you can go to this space and come back to the actual space, right? These things become important when we are looking at, kernels and everything in SVM's sort of algorithms. Okay, we'll go quickly over this idea of eigenvectors and eigenspaces in this in the idea of vector spaces and transformations. Okay, so we say that T be a linear transformation, that is here a linear operator on V. We say that alpha is a eigenvector of T if T of alpha is equal to lambda alpha, right? So if you see here, T is taking a vector from V to V, right? So T of alpha is going to be a vector in V, and we're saying that T of alpha should be equal to some scalar multiple, that is a scalar belongs to the field F, some scalar multiple of the same vector of which it was applied on, right? It's equal to T alpha. Now, if this is the case, we say that alpha is an eigenvector of T, and we call lambda as the eigenvalue of T corresponding to the eigenvector alpha. Okay, Now we'll look at some examples of this operation. So let's say we have V as the set of infinitely differential functions, let's say which go from R to R, right? F goes from R to R, and we already saw that D is basically a linear transformation on this particular set, right? We saw that if I define D of some function G, right? So it's you know if I were to define the differential operation like this, D times Cg of Cg plus F, this will be equal to C times D of G plus D of F. So we know that D is a linear transformation on this vector space V, right? Then if you look at this G of x equal to e power lambda x, right? This function is a eigenvector for this transformation D with eigenvalue lambda, right? And to see that, you can see here, so dg of x is basically d of e power lambda x. We know what is d by dx of e power lambda x, right? This is basically lambda times e power lambda x. E power lambda x is by definition g of x, right? So we got a function that is g, which is a eigenvector, right? G is the e power lambda x is the eigenvector, right, of this operation D, which is defined on a set which is over a set of all functions which are infinitely differentiable, right? So this is one example of eigen vectors in function spaces, right? Then let's say we have this simple theorem here. So we have a transformation T which goes from V to V. So if alpha is an eigenvector with eigenvalue lambda, then so is C alpha, where C is some scalar drawn from field F, right? This field F is over which V is also defined, right? V is defined over F, right? So we need to go ahead and so let's say this proof is again straightforward. We'll do it. So here it is. Yeah. So we're saying that T of alpha is lambda alpha, right? So now T of C alpha is what? We know that by property of linear transformation, this is C times T of alpha. T of alpha is C times lambda alpha, which is lambda times C alpha, right? See, you need to be a bit careful here. This C is multiplying the lambda alpha vector. Lambda alpha is basically the scalar multiplication operation. This is also a scalar multiplication operation. Now I can exchange these two because of the idea of, because this basically turns out to be C lambda times alpha, right? This is from the compatibility operation property, right? C lambda, it can be written as lambda C, right? Because of commutative property, right? Now this can be written as lambda times C times alpha, again from the same compatibility operation, right? So therefore this is equal to lambda times T of alpha. Sorry, lambda times lambda times C alpha, right? So therefore C alpha is also a eigenvector of this T with the same eigenvector with the same eigenvalue lambda, right? So what does this tell us, right? So what does this tell us? It tells us that for a given eigenvalue, let's say lambda, I can have infinitely many eigenvectors, right? Because this C can be any scalar in F, right? So for a given eigenvalue lambda, I can have infinitely many eigenvectors, right? Because I just need to find that one alpha and then keep on applying C alpha over it. All of those will actually be eigenvectors of the transformation T, right? See, either this will happen or I will have just one eigenvector, right? Which will be the trivial eigenvector, which is 0, right? See, we know that for any linear transformation, we saw that T of 0 will be equal to 0, right? We proved this in the last lecture, right? So T of 0 will be equal to 0. Now this I can write it as, so for any eigenvalue, so for any scalar lambda in F, right, I can write this as T of 0 is equal to lambda times 0, right? So for any for all lambda belonging to capital F, right? So either this will happen, right? So I'll be able to find eigenvector, right? Some non-trivial eigenvector, so which will basically make me that all of these C alpha will be eigenvectors, or I will just have the trivial one, which is 0, right? So generally we don't consider the 0 to be an eigenvector as such, at least in matrices. We'll come to it, what are the implications of taking this 0 eigenvector and so on when we come to the last lecture of the course. Okay. Okay, so we saw that for a given eigenvalue lambda, we can have many eigenvectors, right? So now we'll define something called as a v lambda, which is something like this. We say that, okay, let T be a linear transformation for any lambda belonging to F. We'll define a set v lambda which goes like this. So any alpha in V such that T of alpha is equal to lambda alpha, right? So basically the idea that alpha is a eigenvector of this transformation T. Then we want to prove that V lambda is a subspace of V, right? Now remember the subspace theorem, how to prove something is a subspace. We need to prove that, let's say if W is a subspace of V, right? We need to prove that if there are any two vectors in W, alpha and beta, then alpha plus beta should belong to W. And for any scalar C from the same field of F, C times alpha should also belong to W, right? So we'll take a look at that. So let's say we have T alpha 1, alpha 2 belonging to V lambda, right? Then what is T of alpha 1 plus alpha 2? This is equal to T of alpha 1 plus alpha 2 by definition of linear transformation. Again, T of alpha 1 and is equal to lambda alpha 1, and this is equal to lambda alpha 2 because of the fact that they belong to this particular set, right? So by definition again, this is equal to lambda times alpha 1 plus alpha 2. This is from the distributive property, right, of scalar multiplication over the vector addition, right? So this is true. So hence we see that T of alpha 1 plus alpha 2 is lambda times alpha 1 plus alpha 2. So therefore alpha 1 plus alpha 2 is a eigenvector of T with the same eigenvalue lambda. So therefore this will also belong to V lambda set. Okay, same thing here. We know that we just saw previously that if alpha belongs to V, T of C alpha will be equal to lambda times C alpha, which is also again present in this set V lambda, right? We also need one important thing, that is, let's say that V lambda has to be non-empty, right? Now we know that let alpha is 0, T of 0 will be equal to 0. This is by definition of linear transformation. This is equal to lambda times 0, right? So therefore alpha equal to 0 will always belong to V lambda. So any lambda you take, V lambda will always have this 0 vector. Therefore V lambda is non-empty. If V lambda is non-empty and both of these conditions are true, therefore we say that V lambda is a subspace of V, right? So V lambda is basically termed as the eigenspace belonging to the eigenvalue lambda. Okay, so this is the eigenspace. Now, so therefore the eigenspace as such, okay, the eigenspace as such can either be the 0 subspace, right, which is what I spoke about here, or it can be some non-trivial subspace, right? Now we'll see how these two properties come into play when you work with matrices. Okay, then we have, I think, one main theorem here which says like this. So let's say we have T, which is a linear transformation. Let V1 to Vm be the non-zero eigenvectors of T, right, with eigenvalues lambda 1, lambda m respectively. So they're non-zero eigenvectors, right? So non-trivial ones, and with eigenvalues lambda 1 to lambda m respectively. Suppose that these are distinct. This is important, right? They are distinct. Then we say that v1 to vm are linearly independent. Okay, so we'll go ahead and prove it in a while if we have some time remaining. Then okay, so we basically have a set of linearly independent vectors, which are eigenvectors of this transformation T. Okay, now let's say if the dimension of V is equal to n, and there are and I have some transformation T which goes from V to V. If T has eigenvectors v1 to vn such that lambda 1 to lambda n are distinct, then v1 to vn is a basis for V, right? Why? So from the previous theorem we saw that if lambda 1 to lambda n are distinct, we know that v1 to vn are linearly independent. Correct? If these are linearly independent, what does it mean? It means that the subspace spanned by this set, right, has dimension n, right? If this has dimension n, and we know that it's going to be a subspace of V, right? This means that S has to be equal to V, right? That means this set is basically going to be a basis for this vector space V. Okay, this will basically become important when we look at matrices again. The idea that if I can find n vectors, okay, n vectors for a matrix, I can actually span all of its column space with these n vectors, right? And if these are eigenvectors, then that's even more on the cake, right? So this is the idea when we link it to matrices. Okay, then okay, so one example here, let's say we have V is a set of infinitely differentiable functions f going from R to R. Consider that these are the differentiation operation, right? So we know that D is a linear transformation, right? We also know that now D square will also be a linear transformation, right? Why? Because D square is just D of D, right? And we know that if U and T are linear transformations, UT is also defined to be a linear transformation. So D square is going to be a linear transformation, right? Now I'm saying that can you find some examples of this of the eigenvalue of the eigenvectors of D square? Okay, so see, D is defined on the set of infinitely differentiable functions. What you need to do is you need to look at D square by dx square of some f of x. This should be equal to some scalar times f of x, right? Some scalar times f of x. So see some examples of f. We already have one example in this page. Some more examples you can think of, and we'll discuss in the next lecture or something. Okay, so this is the stuff that I want to cover as part of the course. Now we'll do one thing. We'll go back to the pending items here and there, and then we'll go away. We'll do proofs, each of them pending proofs rigorously. So first thing what I want to cover is the basis and dimensions idea, right? So again, just a small recap of what we were doing here is that we are trying to first we saw something called as what is linear dependence and linear independence idea, right? So if I have a set of vectors alpha 1 and alpha 1 to alpha n which are distinct, and I have scalars c1 to cn which are not all zero, then if I can find a set of scalars ci such that this linear combination is zero, then I say that these are linearly dependent. Otherwise I say it's a linearly independent set, right? We also saw what is the consequence of this definition. That is, for example, let's say if any set contains a linearly dependent set, then that set becomes linearly dependent. any subset of linearly independent set is going to be linearly independent. Any set which contains the zero vector is going to be linearly dependent. We saw that because I can just write as any vector can be written as zero, some scalar times zero. Then I have this uh, set of if this set of vectors A is linearly independent, then each finite subset of this set is linearly independent. Okay, so we use this property in proving one of the examples. You know, the given set was linearly independent or not, right? We then define basis, right, as a set of linearly independent vectors which span F, right? We already know what spanning means, right, from the idea of subspaces. So spanning basically means that you're able to cover all the elements of the particular set, right? So basically the set of all linear possible combinations, and we're saying that if this set spans V, then we can say that this particular set is a basis for this vector space V, and the dimension of V is then defined as the number of elements in that basis, right? Then we saw some examples of vector spaces, dimension examples. For example, we know that if F is a vector space, we know Fn is a field. Sorry, if F is a field, we know that Fn is a vector space, and we saw that the dimension ends up being just the number n, right? Hence, we have this axis theorems. So for example, let's say we have your R2 space or R3 space. We see that they are dimension 3 because of the fact that we can find 3 independent vectors, right, which are your Cartesian axis x, y, and z, and hence the dimension idea becomes the dimension of R3 space is basically 3. We also saw an example on the space of all polynomial functions over the field F, and it's so that the dimension of this vector space is infinity, but it has a proper basis for this particular vector space, right? And we saw that basically the idea of this comes from this Taylor series, right, where you can express any differentiable function as a summation over the functions defined in this way, where it is x power k, right? So it's basically your power series expansion, right? And all of these vectors defined as x power k become the basis for this new space, right? Okay, so we saw that, and then we have this idea of so in case we have a vector space which is spanned by a finite set of vectors beta 1 to beta m, then any independent set of vectors V is finite and contains no more than m elements. Okay, so with this we'll go to the two corollaries. Yeah. Okay, so first things first. So let's say we have this idea here. Okay, so at V be a finite dimensional vector space, it is let n be dimension of V. Then any subset of V which contains more than n vectors is linearly independent. No subset of V which contains fewer than n vectors can span V. Now, we saw previously that any subset of V which contains more than n vectors is linearly dependent, right? Because we know that if V is finite dimensional, that is n, so V is finite dimensional, we saw that dim V is equal to n. If that's the case, any two bases, right, any two bases have same elements, same number of elements, right, which is equal to n. We're saying that if any subset of n which contains more than n vectors is linearly dependent. So let's say I have a set. We'll prove the one first. Let's say I have a set S which contains some vectors. I'll use beta here. So beta 1 to beta m, let's say, where m is greater than n. Okay, so we want to prove that this is linearly dependent. Now we know that if n is the dimension of V, then that means I can define a basis set B, which is alpha 1 to, let's say, alpha n, which are linearly independent and span V, right? If they are spanning V, that means I can define any I can basically form I mean all these vectors can be represented as a linear combination of these alpha 1 to alpha n, right? So we say that beta 1 is going to be some summation over alpha I c1 I, for example, right, over all the I, and similarly all the other betas, right, c2I alpha I and so on, right? So if these have to be linearly dependent, so what do I need to prove is that beta yeah, so I need to prove that some combination of these betas c okay, I'll use b1 b2 beta 2 and so on, right, will be equal to 0, will be equal to 0, and there exists some b1s to bm's like this, right, which are not all 0, right? Okay, that means at least one of them will have to be non-zero. Okay, so if this is true, what does this mean, right? So I can write yeah, so this is basically summation over j equal to 1 to m bj beta j. This is equal to summation over j equal to 1 to m bj is, I mean, bj is bj, beta j becomes summation over I c j I alpha I equal to 1 to n. This becomes equal to summation j equal to 1 to m I equal to 1 to n bj c j I alpha I equal to 0. So we need to prove that there exist some values bj which are not all 0 to prove this, right? So this basically will follow from the result that we yet to prove from here, right? We saw that here we said that if we have a product like this, right, where I have I equal to 1 to m, j equal to 1 to n, here more than, so n is more than m here, right? Yeah, n is more than m, right? So if I have a sum like this, okay, this will surely be 0, okay, otherwise it will surely be non-zero. I'll have at least something which is non-zero, right? So this basically turns out to be j equal to 1 to m I equal to 1 to n cj I bj alpha I. So this particular product we're looking at, this particular sum we're looking at, right? So here I can prove this in the matrix theory part, right? So we'll see that this particular operation will always lead us to some or the other bj to be non-zero, right, with this whole system here. Okay, so hence we'll prove that. So from a result in matrix theory, we get that bj's are not all 0 for all j, right? Oh, sorry, there exists one j such that bj is non-zero. Okay, there is one thing. Second thing what we need to prove is no subset of V which contains fewer than n vectors can span V. Now this is a bit straightforward in the sense that to span, so if you want to span V, you need same number of vectors as your basis, right? Right, so basis set here actually has n elements. Okay, so if you want to span V, you need to be able to express every element as a linear combination of these vectors, right? So let's say I have a set S which is beta 1 to beta m. Okay. If let's say and the fact that m is less than n, if we say that beta S spans this basis, spans this V, right, then this would mean that the dimension of V, right, would be equal to m and not n, right? But which is not true. So hence we say that any set which is having less than n elements cannot span V at all, right? That's the sort of thing for this, right? Okay, next moving to one lemma. Okay, so we will use these the following lemmas and theorems or whatever for proving the ranked early theorem of the linear transformations. Okay. Okay, so we have this lemma which is that let S be a linearly independent subset of vector space, that is V. Suppose beta is a vector in V which is not in the subspace spanned by S. Okay, so S by default is a linearly independent subset. Okay, linearly independent subset. Okay, and beta is a vector which is not in the subspace spanned by the set S, right? Then the set obtained by adjoining beta to S is linearly independent. So we are saying that if I add this beta vector to this S, then this set is again going to be linearly independent, right? Okay, so I'd say we have a set which is alpha 1 to alpha n. Beta is not in the subspace spanned by S, right? If it is not in the subspace spanned by S, that means I cannot write it as a linear combination of the elements in S. That means I can write beta is not equal to Ci alpha I summation over I, right? So therefore, any multiple of beta also, that is for some b in the field F, so b times beta will also not be equal to this summation, right? where I multiply b with all of the vectors, right? So therefore I can write this as that I can write this as this minus beta b is not equal to 0, right? So taking the additive inverse on both the sides. So therefore this says that this set is linearly independent, right? Why? Because I cannot find any scalars ci and b such that this will be equal to 0, right? I'm saying, see, for all b this is true, for all ci this is true, right? So therefore this thing will hold for all b and ci, right? So there is no trivial solution. I mean, obviously we have a trivial solution with ci where all ci is 0 and b is 0 and all of that, right? So except this trivial solution, there is no other solution of this b and ci's which can give me a 0 vector. So hence this set becomes linearly independent, right? Now this is a very powerful theorem in the sense that if you want to keep growing your subspace, right? So let's say you have a vector space V and you have some vector space alpha, some vector alpha in this set V, right? Which is a non-zero vector, by the way, non-zero vector, right? If you want to keep growing this set such that you want to span the vector space V, what you need to do is keep on doing iteratively, keep on finding at least one vector beta which is not spanned by this set S, right? And once you find such a vector, update this S to be S union beta and repeat the process until you get the number of elements in S to be equal to the dimension of V. In case you know V, okay, in case you know the dimension of V, keep on doing this until you get a number of elements in S to be equal to this particular set, right? Okay, so this basically gets used in some theorems or some ideas of machine learning like PCA and stuff, where you in PCA, where you keep on building the principal components one after the other, and which try to explain the variance of your data. Okay. Anyway, these are all just side notes of the use of these sort of theorems. Okay. Then we have something called as so the next theorem is basically, if W is a subspace of a finite dimensional vector space V, um, every linearly independent subset of W is finite and is part of a finite basis of for W. Okay, so let S be any independent of subset W. So okay, so what are we saying? We're saying that W is a subspace of finite dimensional vector space. So I have, let's say dim V is equal to n, which is finite. Okay, and W is a subspace of V. Every linearly independent of subset of W. So I'm taking a subset of W again here, right? Let's say I have some S which is a subset of W. This uh, so it's a subset and it's linearly independent. Okay, so what we're saying is, we're saying that S has to be a so this will be finite. This will be finite and is a part of it's a part of finite basis of W. Okay, so first thing, let's see here that let S be any linearly independent subset of W. So this implies that S is a linearly independent subset of V, right? This implies that the number of elements in S is going to be less than dimension of V, right? Why is this? So we already saw from this corollary, right? So can span V. So from this theorem, right? So any independent set of vectors in V is finite and contains no more than m elements. So the number of elements in S, which is a linearly independent set, is going to be less than dimension of V. Dimension of V we know is finite, so therefore S has to be also finite. Okay, so this part is clear. The second part is basically, let's say we have a vector beta 1, which is a vector of W, but which is not spanned by S. Okay, so we construct a set S1, okay, which is just S union beta 1. Okay, now continue this process until the set spans W. Now see, we know that this S1 will be a linearly independent subset of of this space W, right? From this theorem, from this lemma we just saw. So so this S1 now has so let's say if n was, let's say n m dimensional if the number of elements of S was m, now S1 will have m plus 1 elements, right? So what I will do is, I'll keep on going ahead with this process over and over until I find a set, okay, S1, which spans W, right? Which spans W. Why will this happen? Because the number of elements of S is less than the number of elements in W, right? Because we said that it is linearly independent subset of W, right? So we keep on doing this until we span W, right? So now what I have is, I have a set which is spanning W and is linearly independent, right? Which is by default the definition of a basis, right? So the initial set S was now a part of the basis of W, right? So therefore we say that this particular subset, right, is a part of is a part of the finite basis for W, right? This is the theorem proof. Okay, so here the idea is that we are constructing a new set over and over by adding vectors which are not spanned by that particular set. Hence, the number of the subspace spanned by that particular set will also increase. We keep on doing this until we span the actual subspace W, right? And once we do that, we have a set which spans W and is also linearly independent. So by definition, it is the basis for W, right? And therefore, since it contains a set S, because we started from the set S, therefore your set S will be a part of the basis. Okay, so that's the idea. That's the theorem. We'll come to two corollaries. So first thing is, let's say if W is a proper subspace of finite dimensional space V, then dim V is strictly less than dim W. So what does this mean? Proper subspace in the sense, just the idea of proper subset taken. So we know that subspace is basically defined like this, right? So W is a subspace of V. Proper in the sense, there is something missing, right? So this is the idea. Now we're saying that the dimension of W should be less than or equal to should be less than strictly less than the dimension of V, right? Now we say, see, it can either be equal or less than. It cannot be more than, which we know for sure. Now the thing is, we want it won't be, if it is equal. If it is equal, then we say that the I have a set, right, which spans W and V, right? This will be true if dimension of V is equal to dimension of W, right? If this spans W and V, that means your so what is set spanning any subspace mean, any space mean, right? So that means this W will be set of all linear combinations of the set defined by S, which will also be the set V, right? But we say that V has to be W has to be a proper subset, right? So proper subspace. So if this is true, this cannot be true, which means this cannot be true, right? Therefore, dim V has to be less than equal to less than dim W. Okay, so hence this follows from the previous theorem. Next corollary is this. So in a finite dimensional vector space V, every non-empty linearly independent set of vectors is part of the basis. Again, very straightforward idea. So what are we saying here? We're saying that in a finite dimensional vector space, so V is going to be finite dimensional. So dim V is, let's say, n. We know for a fact that if dim V is n, then any set which is linearly independent, okay, which is linearly independent, will have at most n elements, right? At most n elements. Anything more than this will make the set linearly dependent. Now when that happens, so we're saying that, okay, so this set has at most n elements. Let's say with this set is S, and this it has about m element, which is less than n, is not equal to n. We saw that if I have a finite dimensional set which is again linearly independent, right? If this is true, then we know that it's a part of the basis, right? Why? From this theorem, we just saw that if it is finite, right, it's also a part of the finite basis for W, right? Where here we're saying that W is just V, right? Because any vector space is a subspace of itself, trivially, right? So hence this particular set S is a part of basis. Is a part of the basis. Okay, fine. So this is what I had planned for today. We'll go to this idea of coordinates in case. Yeah, we'll finish off these vector spaces or spaces coordinates. Yeah. So coordinates. Okay. So here the idea is that we know what is a vector space, right? So let's say we have a V, which is a vector space. we know the idea of basis. Let's say I have a B, which is a basis for this vector space, basis for V, which means that I have some, let's say alpha 1 to alpha n, some n vectors of this vector space which span V and are linearly independent. Okay, and are independent. Now the idea of coordinates is, so what I will do is I will define this B in a bit different way. I'll say, okay, I will order these vectors uniquely. Okay, so I will represent B now as a set, as a list, alpha 1 to alpha n, alpha 1 to alpha n. Okay, now let's say I have a vector beta in this vector space V. So we know by definition of the basis that I can actually find some scalars, right, Ci belonging to the field F, such that Ci alpha is equal to this vector beta, right? So then what we say this set of Ci, this list of Ci, I going from 1 to n, is the coordinate of the vector beta under the basis B. Okay, and I will use a script sort of a thing to say it's an ordered basis. Okay, so this is called the coordinate of beta under the basis B. Okay, now this is very similar to the idea of coordinate in a Cartesian coordinate system that we have learned before, is comes basically from this idea, right? So let's say I have the R2 space, right? So I have a xy plane, right? We say that any point in this plane is, let's say, some a comma b, right? So what are we actually saying, right? So we are saying that this a comma b is the coordinate of this particular vector, the vector being a times the e1 vector plus b times e2 vector, where e1 is basically 1 0 and e2 is 0 1, which is your standard basis. We discussed this in this basis lecture, standard basis of Fn, right? So when that happens, so we are saying that this vector, let's say some vector, let's say I'll call it as gamma. So this gamma is basically a times e1 plus b times e2. That is the linear combination of these two vectors, the basis vectors e1 e2. So I can represent this gamma using these two numbers, that is a and b, right? So this ordered list or set or tuple basically is the coordinate of gamma under this basis e1 e2. Okay, so with this you have seen, this idea under B is very important, right? So so this actually, if you want to be more mathematically precise, what we say is, we say something like this. We say it is over in the set under the basis B. Okay, now let's say, so which begs the question that in case I want to let's say change the basis, right? So we know for a fact that, let's say if I have a basis B1 and basis B2 of a vector space, right? It doesn't imply that B1 has to be equal to B2, right? Because I can have two different sets spanning the same vector space, right? But what has to happen, that we already saw, is that the number of elements in this two sets have to be equal, right? Which we know from the basis and dimensions theorems, right? So let's say for now that this is a finite dimensional vector space. So we say that b1 equal to b2 equal to n. So now let's say I have some vector beta, which belongs to this vector space V. Okay, I will define this B1 as, let's say, alpha 1 to alpha n, ordered list again, and beta 2 as some gamma 1 to gamma n. Sorry, gamma 1 to gamma n. Okay. Now, since both of these are bases, I can actually express beta in any of these two bases, right? So, in both of these bases, so I can say beta is equal to some I, ci alpha I, and the same beta is equal to di gamma I, right? Di gamma I. Okay. So now the question becomes like, so let's say if I want to move from some basis to another basis, how do these coordinates change, right? Because now the coordinates of beta under this basis is going to be ci, here is going to be di, right? So 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 the question is like, can I form some relation between ci and di? Now let's say if see, since B2 is also a basis for the vector space V, and alpha 1 to alpha n are vectors in V again, so I can represent alpha 1 and each of these alpha i's as linear combinations of gamma I and gamma 1 to gamma n, right? So therefore, let's say I represent alpha I, okay, as some combination of okay, I'll use gamma j here. Okay, gamma j I equal to 1 to n gamma I. What numbers do I use? Let's say I use a ij. Okay, so this is the so therefore your aij becomes coordinates of the vector alpha j in this basis b2. Okay, now if I were to put this here, what do I get, right? I get beta becomes summation of I equal to 1, let's say j equal to 1 to n cj alpha j, right? Again, just by definition, this becomes j equal to 1 to n cj times, what is alpha j? Alpha j is I equal to 1 to n aij gamma I. Okay, this becomes j equal to 1 to n c I equal to 1 to n cj aij gamma I, right? These two sums are finite, so finite sums, so I can exchange them, right? So I equal to 1 to n, j equal to 1 to n cj aij gamma I. So now I have represented beta again as a this is some number, right? This is some scalar belonging to f, right? Which is basically just this di. Okay, so di, that is the new coordinates, okay, are just going to be j equal to 1 to n cj aij. Okay, clear? Now this I can write in a matrix sort of a fashion, something like this, right? I can write this as, so let's say if I what do we do here? I can do it like j equal to 1 to n cj, yeah. So I can write this as two vectors, right, in f n space basically, the vectors being aij, okay. Let me just put this like this, yeah. So a1j, sorry, not a1j, it will be ai1 and so on. So ai1, ai2 and so on up till ain times, okay, I mean the dot product of this and the vectors, I mean the vector defined like this, c1 c2 until cn, right? Okay, so if I were to represent, let's say this di as a vector, okay, so let's say I have d, I define it as a vector d1 to dn, okay, this can now be represented as a matrix multiplied by this vector c1 to cn, so c1 to cn, right? Each of these will now become a11 up till a1n and so on, an1 up till ann, okay. So I can just write this as let's say I call this as c, okay, so where c is just a list of all, I mean the vector of this type, right? So what are we saying here, right? So we are saying that if I want the coordinates, okay, of any vector beta, okay, in some in some basis, let's say b 2, okay, b2, right, which is d here, right? So the coordinates of any vector beta in b2 in some basis b2 is basically just the I'll call this as yeah, so I'll call this as a matrix. Notations are a bit unclear. One second, this I can call it as um, a, okay, this is taking you from 1 to 2, so I'll write it as 1 to 2. Okay, see, I'll get the exact notations by the next class. Okay, so what we're saying here is that we're saying if you want any coordinates of some vector beta in b2, you need this sort of a matrix, right? 1 to 2, right, multiplied with the coordinates of the same vector, coordinates of this vector beta in b1 under the basis b1, right? Okay, so what is this a talking about, right? So a is saying how should you convert, how will you convert the elements of two bases in the first place, right? So see, we're saying that alpha j is the element in basis b1, gamma I is the element in basis b2, right? So if I want to go from the elements of yeah, if I want to go from b2 to b1 to b2, I need to know how to convert my basis vectors themselves, right? So this is basic, this a matrix is called the coordinate transformation matrix, right? In some sense, coordinate transformation matrix. So what are we doing here? We are looking for the coordinates, right? Coordinates of the basis vectors among each other. Okay, so if you can find such a matrix, right, if you find such a matrix, then you can take any vector in vectors coordinates in some basis b1 and move it to some other basis b2. Okay, now this is the basic idea of when you see and talk about things like your rotational transformation matrices and all of that, right? So for example, let's say I'll take a simple example. Let's say R2. Let's say I'll define B1, okay, as a basis, which is let's say I'll call it as ordered basis. Okay, so I'll say this is 1 0, comma 0 1, right? And I want to use another basis B2, right? So see, for this to be a basis, it has to be linearly independent, point number one. Point number two, it should span the whole vector space R2, right? So let's say I'll use 2 3 and then 3 2 should be sufficient, I guess this is a basis, right? Because okay, so if you want to prove this is a basis, first thing is there linearly independent very clearly, right? Because what happens here is you want to be able to so you cannot represent any of them as the multiple of the other, so it is linearly independent, which is fine. Second thing is, does this span the whole vector space, right? So any vector, let's say some a b, right? Can I obtain this from uh, the linear combination of this one, right? So I get 2c plus 3d, 3c plus 2d. Okay, so what are we saying? We're saying, okay, this actually can be written as 2 3 3 2 times cd, right? So we're saying, is this matrix, okay, when multiplied with all vector, all possible combinations cd, will it produce all the possible combinations a b? Okay, right? So I'll leave it as an exercise for that, this proving that this is actually a basis. I mean, this actually happens. Okay, so here you need concepts like matrix invertibility. Okay, and system of linear equations. So we won't cover that in this course, at least for now. And so when you use this, you'll see that this is basically a vector, a basis for the same R2 vector space, right? So now what we're saying, okay, if you have this, uh, can you represent vectors, the basis vectors b in some sense as in b1 to b2. Okay, so for example, let's say I have a vector xy, okay, in R2. Okay, so the coordinate of xy under b1 is very simple, right? So the coordinate of xy, let's say I'll call this vector as x. Okay, so the coordinate of x under b1, okay, under b1 is just x and y, right? Now if I want to move this to the basis b2 space, okay, b2 space, what do I need to do is basically look at how can I transform these vectors in this space. Okay, yeah, so okay, so what I need is basically something like this. So I need the elements. So in the same format, what I need to do is I need to find out if I want to transform, right, the elements 2 3 so express these vectors in this basis. Okay, so that is basically 1 0. Can I express this as some coordinates? Let's say in this case, this is, let's say, alpha 1 alpha 2. This is what we use symbols here, gamma 1 gamma 2. Okay, so this is gamma 1 gamma 2, right? So I'm looking at alpha 1 right now. So the this one is a 1 1 aij. So a 1 1 and a 2 1, right? Yeah, a 2 1. Okay, so we basically want a11 a21 such that these will basically map my element, the vectors alpha 1 in this basis, right? So basically if you will do this matrix inversion here, okay, this will turn out to be just the inverse of this. So 2 3 3 2 matrix inverse times 1 0, right? So matrix inverse here will be defined as 4 minus 9 is minus 5. This will become I think 2 2 minus 3 minus 3 ls times 1 0, right? When you do 1 0 here, so you get 2 times, so this will become 1 by minus 5 times 2 and minus 3. Okay, so this is basically minus 2 by 5 and 3 by 5. Okay, so these are the values for a11, a21, right? And then similarly a21 and a12 and a22, you can define you can get in the same way. So 2 3 3 2 inverse times 0 1. Okay, you will get some value here. Now what you do is you say, okay, when I have this vector alpha xy here, okay, so if I want to convert this into the coordinates under the basis b2, okay, so you take this matrix, so your coordinates now, let's say if I define the coordinates as u comma v, right, this will be just equal to the matrix multiplied here, I mean the matrix that we obtain, a11, a12, a21 and a22 times xy. Okay, so when you do this, you will get some u and v. That will be your new new coordinates of the same vector under the basis b2. Okay, so in case, so let's just go ahead and solve this. You will get a complete idea. So 1 by this minus 5 times 0 1, this becomes so 3 by 5 and minus 2 by 5, right? Yeah, so this becomes basically a11 is minus 2 by 5, a12 is 3 by 5, this is 3 by 5 again, minus 2 by 5 times xy. Okay, so u basically is minus 2 by 5 times x plus 3 by 5 times y, and v is basically 3 by 5x minus 2 by 5 y. Okay, so this are your new coordinates of the same. So any vector xy you take, defined in under the basis b1, its coordinates under b2 is going to be minus 2 by 5x plus 3 by 5y, comma 3 by 5x minus 2 by 5y under the basis b2. Okay, so this is the idea of coordinates and coordinate transformations. So this idea basically you can go and extend to looking at things like moving from Cartesian coordinates to polar coordinates, sort of a thing, right? Polar coordinates, all of these. So all of these are well defined transformations which basically use this idea, right, where you can define any vector in any basis, right, and to move from one basis to another, what you need is just how you need to transform the actual basis vectors among themselves. And once you have that transformation, once you have that mapping with you, you can always transform any vector in one basis to another basis, right? So this is the idea of coordinates and coordinate transformations. With this, we complete vector spaces part of the so from until here we completed. Linear transformations will start in the next week. Okay, I can complete these two parts. These are simple. Next class we'll just directly jump into rank nullity theorem. Okay, so this thing was pending, right? So let's just complete of this simple thing. So okay, so in this linear transformations, we saw that we have two important subspaces for any linear transformation. That is basically range and null space, right? So range of T is basically defined as any vector in W which I can reach from T, right? So there's some pre-image existing in the set V, right, which when applied T upon gives me beta, right? Okay, so what we want to prove is we want to prove that this is the subspace of W, right? So how do you prove something in subspace? We say that let's say alpha and okay, let's say gamma 1 and gamma 2, okay, are belonging to this R of T, right? belong to R of t, right? What we need to prove is we need to prove that gamma 1 plus gamma 2 also belongs to R of t or not. That's the first thing that we need to prove. So how would we go about doing this? So we know, so if they belong to R of t, right? So which means that there is some, let's say delta 1, delta 2, right? So t of delta 1 is gamma 1, right? And t of delta 2 is gamma 2, right? So where gamma 1, gamma 2 belong to W, right? Because that's the range of, codomain of T, and delta 1, delta 2 belong to V, which is the domain of T, right? So, so with that in mind, so now I know that I can look at T of delta 1 plus delta 2, right? Now this is equal to the T of delta 1 plus T of delta 2, right? Why? Because it's a linear transformation, right? By definition this is true. Now what is T of delta 1? Gamma 1. Delta 2 is gamma 2, right? So therefore which again belongs to W, right? So gamma 1 plus gamma 2, which is an element of W, has a pre-image in T, which is delta 1 plus delta 2. Okay, so therefore gamma 1 plus gamma 2 will belong to the R of T, because this can be reached from T, right, for some delta 1 plus delta 2. So this belongs, therefore this belongs to R of T. Now similar idea you can use to prove that a scalar multiple is also there. So for example, let's say I have a gamma which belongs to the range of T, okay, and there is some C which is a element of field F, right? And we need to prove that C gamma also belongs to R of T, right? So now just consider C of T of C. So if gamma belongs to R of T, that means there is some delta T of delta which is equal to gamma, right? Where delta belongs to capital V, right? So therefore, so now consider T of C delta, which is equal to C times T of delta, which is equal to C times gamma, right? So I can reach C gamma from C delta on through T. Therefore, C gamma belongs to R of T, right? So hence by the definition of this this system, okay, so one thing is pending here. We need to prove that R of T is non-empty, right? So any idea, we know that for a fact that T of 0, right, T of 0 is always 0. We know this from the claim that we made in the same page, right? So we know that T of 0 is always going to be 0 if it's a linear transformation. So if that is true, what does this mean? This means that R of T is non-empty, right? Because I can always reach 0 vector from 0, so therefore 0 will be will belong to R of T, right? So hence, R of T is non-empty. So if R of T is non-empty, and for any two vectors in R of T, their sum belongs to the set, the scalar multiplication belongs to the set. So from this we know that R of T is a subspace of W. Correct? From the subspace definition theorem. Okay. Then the next theorem is to prove. Next thing is to prove is that the null space of any transformation T is a subspace of B, right? So here, let's say I have two vectors, again gamma 1, gamma 2, which belongs to null space of T. This implies that T of gamma 1 is 0 and T of gamma 2 is 0. Which implies that T of gamma 1 plus gamma 2, which by definition is T of gamma 1 plus T of gamma 2, is 0 plus 0, which is equal to 0. So therefore this implies that gamma 1 plus gamma 2 belongs to N of T, right? This is one part of the proof. Second part of the proof is that, let's say if gamma belongs to N of T, okay, this implies that T of gamma is 0 by definition of N of T. Now consider some vector, some scalar T is C of T of C gamma, is C times T of gamma, which is a C of C times which is equal to C times 0, which is equal to 0, which implies that C gamma belongs to N of T, right? So this is done. Now we need to know that if N of T is non-empty, which is true. Why? Because T of 0 is 0. This implies that 0 is belongs to N of T, right? So therefore N of T is non-empty, right? And therefore from subspace definition theorem, we know that N of T is a subspace of V. Okay, and we define some definitions like rank, what is rank and what is nullity of a transformation T, right? And we define the basis and all of that, right? Okay, so so with this we'll stop today's lecture. So we will have a special lecture on Sunday where we will do this rank nullity theorem. That is one that is pending in linear transformations. In algebra of transformations, we have some proofs we need to complete on this inversion and stuff like that. After this, we will purely work on some problems, right? Problems regarding subspaces, dimensions, coordinates, and all of these. In the next to next class, we'll either move to eigenspaces and some problems here, or and in the last class will be on how do we relate all of these ideas to matrices, right? Coming from the idea of vector spaces, right? Each of these concepts we will see how we can apply to matrices, right? And how their definitions in matrices can all be subsumed in this idea of vector space linear algebra. Okay, so fine, we'll stop here. See you guys on Sunday 10 a.m.